last class we have seen that in case of discontinuous maps, you have, well, in general it would be something like this. Here is the 45-degree line. In general, it would be a structure something like this, right. So, if you have a map like this, we have seen that even though there is no fixed point, there can still be a periodic orbit, closed bounded orbit. So, this is something that is very peculiar for discontinuous maps, and in order to find out the different orbits, the methodology, essential methodology that we followed was, first we find out whether a period 1 orbit exists or not, depends on whether there is an intersection with the 45-degree line. If not, then does a period 2 orbit exist? The logic was simple. You have got this state space, there is one point to the left, one point to the right. So, this point comes here, this point comes there, and start from here, apply the left hand map, go here, apply the right hand map, come here, and then make x n plus 2 is equal to x n. That when you solve, you obtain the position of this particular point. Similarly, you obtain this particular point, and the condition of existence of the period 2 orbit will be that this will be in the left hand side, x coordinate negative, this will be in the right hand side, that means this coordinate will be positive, and its stability will be given by the Jacobian of the left hand side times the Jacobian of the right hand side. You get a matrix, its eigenvalues. If the eigenvalues are inside the unit circle, it is stable, else not. Similarly, you will probe the possibility of existence of a period 3 orbit, and there can be two types of period 3 orbit, LLR and LRR. So, LLR orbit will be like this, one point here maps to another point here, maps to one point here, and then that fellow maps back. So, in this case also you can obtain in a similar manner this position, this position, this position, but it is clear that it is not necessary to consider this position. Why? Because the possibility that this fellow might violate the condition that this is in the negative side before this fellow is practically none. So, we will consider this particular point being in the negative side and this particular point being in the positive side as the two conditions under which, the two extremum conditions under which you will have this LR orbit existing. Similarly, for LRR orbit you will have one point here, another point here, another point here, and it goes back. In a similar manner you can find out this position, this position, this position, but ultimately the parameter range for which this orbit will be actually occurring will be dependent on this position being in the left hand side and this position being in the right hand side, and we will ignore this position because so long as this fellow is in the right hand side, this fellow obviously is in the right hand side. So, this orbit will have a specific range of existence with the extremum condition being given by this position becoming equal to 0 and this position becoming equal to 0. Similarly, this particular orbit will exist for a specific range of the parameters, and this particular point becoming equal to 0 and this particular point becoming equal to 0, these two are the extremum conditions. Similarly, you can obtain the higher periodic orbits and their conditions also. In general, these might become a bit, if you want to work that out algebraically, may become a bit cumbersome to actually work out by hand. So, in those cases you might take recourse to any of the standard programs that allow symbolic computation. For example, Maple does, MATLAB has a symbolic computation routine. You can use those in order to obtain the exact range for which this will occur. But then you can see that the LR orbit and LRR orbit, these are the two possibilities of period 3 orbit. Period 4 orbit can happen in these combinations L, 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 R, L, L, R R and L R R R. Out of that, this orbit is essentially the same orbit as the period 2, and so we will L L R R are the 2 points L, 2 points R. So, essentially the same orbit as the period 2 orbit. So, when we consider the period 4, we will have to consider these 2 orbits. Similarly, what are the possibilities for period 5 orbit? L L L L R, L L L R R, L L R R R, L L L R R R R. So, 4 possibilities. Similarly, if you try to work out the period 6 orbit, you will find that there are how many? No, it will not be 5, because in between there would be one combination which is L L L R R R, which is the same as the earlier orbit. So, we will discount that and we will take the others. So, similarly, you will see that these orbits will occur for specific ranges of the parameters. Now, here today, instead of considering each case one by one, we will simply talk about the various possibilities and the general methodologies, because otherwise the talk might become a little bit boring for you, because if I keep considering every case, then it will be somewhat difficult for you to digest. So, what I will do instead is that this is the general framework, and with this general framework it is possible to obtain in which parameter range can a specific orbit occur. So, it is not necessary for us to consider each particular case, for example, A side becoming greater than or less than 1, B side becoming greater than or less than 1, and all this is not necessary, because with this framework I can work out if a period 2 orbit will exist, a period 3 orbit will exist, a period 4 orbit will exist, and ultimately for every condition we can talk about that. But there are specific situations which we have already talked about, for example, like this, where you do not have any fixed point, yet periodic orbits will occur. In this condition, we can see from logic that both the sides are stable, their slopes are less than unity, and therefore, unit intervals do not expand, and if they do not expand, you cannot have a chaotic orbit. So, all orbits will be periodic orbits, and all these sequences will occur, and as a result the bifurcation diagram will look like what is shown in this computer screen. So, here you notice that there is a period 2 orbit, there are a couple of period 3 orbits, and so on and so forth, as anticipated from this theory. And in this side there is a period 1 orbit, in this side there is a period 1 orbit. Notice that this structure of the bifurcation diagram is not generally found in other types of systems. This is typical of discontinuous maps. So, the purpose of today's lecture, at least the first part, is essentially to give you a visual impression of the kind of bifurcation diagrams that come from discontinuous maps, so that if you encounter that kind of a bifurcation diagram in any given system, you would be able to intuitively say, okay, I do anticipate a discontinuity in this case. The map, even if I do not know what it is, it must be a discontinuous map if the bifurcation diagram is something like this. So, I will not go to each and every condition individually. Again, I will just try to give you the flavor of the things. I will make it little smaller. Here is another bifurcation diagram that take a look at it. Here, obviously, it is not this case that we just considered, because I can see a chaotic orbit. Now, in order for chaotic orbit to occur, it is necessary that one of the sides will have slope greater than unity, and the other side has slope less than unity. That is why periodic orbits also occur. If both the sides have slopes greater than unity, then you do not anticipate a periodic orbit at all. And as you can see that as you increase the parameter in this case, that then more and more higher periodic orbits are occurring, and then finally it goes into chaos. Notice one thing, that in that case you are essentially, even for from common sense you might say that the site in which the slope is greater than unity, you are having larger and larger number of points in that site, so that beyond a certain periodicity you are having the slope of that high periodic orbit greater than unity, and you do not have a stable periodic orbit in that case. So, in this part you see a chaotic orbit. Again you would see that these high periodic orbits occur, again those things accumulate at certain points. Can you see the hand like thing here? Yes, they accumulate at certain points, so that if you decrease the parameter, you will find that the periodicity is increasing, and at this point the periodicity is actually infinity, even though the orbit is not chaotic. So, this is another typical structure of a bifurcation diagram. Let us go to some other cases. Yeah, here. Can you see the structure then? Here you would see that I have, according to the structure of things that I have just explained, there is a range for which a period 1 orbit occurs, there is a range for which a period 2 orbit occurs, there is a range for which a period 3 orbit occurs, so on and so forth. I can see a clean period adding cascade here, right. But notice that the range for which the period 2 orbit occurs overlaps the range of the period 3. So, there is a range over which there is a coexistence of attractors, and again you have this accumulation of orbits up to this point. See, this is another typical case where you have the accumulation of orbits into a chaotic orbit. So, I am not describing under which condition and other things, because I do not want today to go into each individual case, which you can with this framework work out yourself. For example, there would be a condition when you have a particular range in which only chaotic orbit occurs, and the bifurcation diagram will look very boring, nothing much is happening. Why? Because in this range the behavior is only chaotic. This means that this happens in the case where you have, let me show you that situation, where both the sides are greater than unity, and as a result only under certain condition there will be a situation where the chaotic orbit can be stable. That will happen when you see this is one extremum point, this is one extremum point, when any point inside, let me make it a little larger, it will be easier for you to see then. Any point, this point, when this point maps to a point outside this point, then it goes to infinity. When this point maps to again outside this range, then it goes to infinity, else it remains inside. So, there would be a range of parameters where this orbit, this trap will actually be stable. As a result, you will see a chaotic orbit which is something like this. So, basically the point is, in most cases these can be worked out from this structure that I have just explained. Here also you see the period 1 to period 2 to period 3 to period 4 ultimately landing into a chaotic orbit, or you can also have a transition to chaotic orbit directly. Now, in general, now let us turn our attention to the paper. In general, you have found that in these cases you find cascades, but these cascades are different from the period doubling cascades that you have found in smooth maps. These are often period adding cascades, or what are known as period incrementing cascades, where there are 3 possibilities. Suppose let us consider there would be period adding or period adding, so that there will be a range for which period 2 will occur, there will be a range for period 3 will occur, there will be a range for period 4 will occur, and suppose the ranges are like this. There is a range for period 2, there is a range for period 3, and then so on and so forth. This is one possibility. Okay. Another possibility is where you have period 2 and then period 3. In between these ranges up to what parameter value, here you can either have a mu or tau L or sorry, in this case A or B, any of these can be in the x axis as a parameter, but you can easily find out the range to which this period 2 orbit will occur and the range from which the period 3 orbit will start. In this case also you can find that. The difference between these two is that in this case the two ranges overlap, in this case there is a gap in between. When they overlap, what happens you have seen, when there is a gap in between this range you find a chaotic orbit, because the orbit is bounded. If the periodic orbit is not there, then the only thing that can happen is a chaotic orbit. So, it will be a period 2 orbit chaos, period 3 orbit chaos, period 4 orbit chaos, and so on and so forth. In this case it will be period 2 orbit overlapping, period 3 orbit overlapping, period 4 orbit, and so on and so forth. These are the two very standard sequences, period incrementing sequences that you find in many physical systems. Okay. And the critical case of the situation between these two is where this period 2 orbit ends, exactly there period 3 orbit starts, where the period 3 orbit ends, exactly there the period 4 orbit starts, and so on and so forth. These are the, that will be the critical case between these two, but these two are the generic situations that you find often in physical systems, and that explanation has to come from the actual computation of the parameter range for which each periodic orbit will occur. Clear? So, I am not going into the details of it. The point is that there are a large number of physical systems in which you do anticipate there to be a discontinuous maps. Many people have investigated physical systems where they have obtained experimental or simulational bifurcation diagram that look like these, and then looking at that one should be able to say that okay, now I know that this particular system in some way must be giving rise to a discontinuous map, and then the investigation has to go in the direction of how, in what way, by what logic is this system giving rise to a discontinuity in the map. Similarly, one can also probe the bifurcation behavior in systems that are higher dimensional. That are higher dimensional in the sense that you have a 3-dimensional system, which when you place a Poincare section that becomes 2 dimensional, and in that 2-dimensional system if there is in some physical way there is a discontinuity, you have got a 2-dimensional discontinuous map. Similarly, you can visualize that there can be higher dimensional 3-dimensional, 4-dimensional discontinuous maps also. Unfortunately, those theories are not yet so very well developed, so I am not in details presenting those. But what was the essential logic in probing this? Notice again the essential logic. We said that our investigation of the various types of non-smooth bifurcations are essentially going this way, that we know that in a system there is a boundary, and as a physical system's fixed point is moving, if as changing a parameter, the fixed point is moving and at some point it is hitting the border, then possibly it is going to the other side, then we are locally linearizing it, and we are only investigating the character of the locally linearized map. That was the essential method. And then we said that the whole bifurcation theory relevant for these systems will depend on the Jacobian matrix here and the Jacobian matrix there, right. We had again normalized that Jacobian matrix into the into a matrix containing only the trace and the determinant, but essentially it is the J1 and J2 that matter. Clear? You might ask how to measure the J1 and J2 for any given physical system. Remember, any given physical system means you have some kind of a orbit and you have placed say a Poincare section here, and we are talking about the Jacobian matrix around this particular point. How to obtain it? It is not a trivial problem. It is not a trivial problem. If you are lucky, if you are able to obtain the map in closed form, yes, you can make a Jacobian matrix. But if it is not available in closed form, then what? Then can you obtain or can you not obtain this J1 and J2? If you cannot obtain, obviously you cannot apply the whole structure of the theory. So, it is necessary to obtain the Jacobian matrices in the two sides, and only then you will be able to apply. Why did we need this Jacobian matrix in the first place? In the first place, we needed the Jacobian matrix because what does the Jacobian matrix here tell me? It tells me that if there is a fixed point here, then the character of the fixed point, if you start from an initial condition that is away from it, the way it will go either towards the fixed point or it will go away from the fixed point, the subsequent iterations of that will depend on the Jacobian matrix. That means, when we are considering the local linear neighborhood of that, the subsequent iterates will depend on the Jacobian matrix. Essentially, then the Jacobian matrix will tell about its stability. So, the problem then is to find out its stability. Now, in history, this has developed in certain stages. This idea has developed in certain stages. First, the question was in general run of the control theory. Most of you have attended some course on control theory, that is why you more or less know, and those who are from science background, you have dealt with the same thing in mathematics courses. We are essentially dealing with equilibrium points of a set of differential equations. There we have x dot is equal to f x, where these are vectors, as the given system description, and by putting x dot is equal to 0, we solve this and thereby obtain the equilibrium point, and then the whole gamut of the theory is essentially geared towards what is the stability of this equilibrium point. The whole theoretical structure is for that. And as you know that when we talk about only the local linear neighborhood, it becomes far more convenient to convert this time domain behavior to Laplace domain behavior. So, we take a Laplace transform and do the whole thing in Laplace domain, do the design and everything in the Laplace domain. So, all these things are well developed, but those ideas are related to only equilibrium points in the state space of a continuous time dynamical system. Okay. But here we are talking about closed loops, we are talking about orbits like this, a limit cycle and the stability of the limit cycle. Now, when we are talking about the stability of the limit cycle, obviously it is not the same theory. Stability of the limit cycle cannot be obtained by the same kind of logical structure as you have applied for the equilibrium point of a continuous time system. But here what was the logic? The logic was that if I perturb it, that means if I start the initial condition from somewhere else, then the way that initial condition will either home onto that equilibrium point or go away from it, that will give it stability. Okay. And that in that case was given by the in the continuous time in the time domain description, you have the eigenvalues of that equilibrium point, and we said that that has to be in the left plane. Okay. So, this is the real part and this is the imaginary part, and if it is the left hand side, we said that it will be stable. But in this case the same idea will not work, because here we are not talking about a single point. Whose neighborhood are we talking about? Obviously, then we have to talk about the neighborhood of this whole orbit. It is not the same problem then. Now, the way to deal with that problem is to give a perturbation here and see how this perturbed trajectory evolves. Does it go closer and closer to that original trajectory, or does it move away from it? Accordingly, you will get the answer. So, essentially the question is how the part of trajectory evolves, how the part of trajectory evolves. And the way the question has been probed is something like this. I will bring the other one in picture. Yes. Can you see it? No, I do not want to show it because it is too small. I will write it here. I will write on this on the paper, and it is not necessary for you to see the screen, because this is a little bit smaller font than you would be able to read. Okay. So, what are my starting points? First, we start from initial condition somewhere here. Say this is my state space, and this fellow evolves from that initial condition by some set of equations. And that set of equations, let that be x dot is equal to f of x comma t. It will be dependent on t for non-autonomous systems. It will not be dependent on t for autonomous systems, but in general it will be like this, where x is a vector. So, in future whenever I will write x, just remember that it is a vector. In case of a simple pendulum, it will consist of the vector of the position and the momentum. In case of a electrical circuit, the vector will consist of the voltages across the capacitors and the current through the inductors, and depending on the number of these storage elements in the circuit, it will have n number of state variables. So, these are these x, and the starting condition is x at t naught is say x naught, that is the starting point or the initial condition. Now, starting from here, it goes through a certain trajectory, and if that trajectory is designated by the symbol phi, then you can write phi, which will be a function of time, which will be function of the initial time, and it will be a function of the initial condition, right. And this is written as starting from x naught plus integral of the function, which would be starting from t naught to t, and you will integrate this function f of what? The solution is phi. So, of phi of, again this I will write it as tau, because I will integrate over tau, t naught x naught comma tau, right. So, essentially what I am writing is that my starting point is x naught, and then the integral over the derivative function, that is how I am getting the actual solution. That is how we do it. So, this is the starting point. This is how the orbit is defined. And then what are we doing? We are giving some perturbation to the initial condition, say this much, and then we are trying to find out how does the path trajectory evolve. Essentially, we are asking the question, if I now hold the initial condition and perturb it, move it, if I hold the initial condition and move it, then how much will the trajectory be perturbed? That is the question we are asking. So, if I perturb it, but the trajectory is not perturbed much, even if we perturb it, the trajectory after some time loses that perturbation, homes onto the original trajectory, then it is stable. That is the concept. Okay. So, in order to do that, this is the trajectory, and I am trying to ask the question, how sensitive is my trajectory here to perturbations of the initial condition? How will I quantify that? By taking a derivative of that with respect to x naught. Okay. So, we will take a derivative of this with respect to x naught. It would be I will write in black. With respect to Now, the phi, the right hand side was x naught, and I am taking a derivative with respect to x naught, but x naught is a vector. So, it will yield a identity matrix. So, this will be I, which is the identity matrix, plus integral t naught to t. We have to take a derivative of this fellow. So, we will take a derivative by parts. We will first say that the derivative of f of phi of t naught x naught, have I closed all the brackets? Yes, with respect to at x equal to x naught times can you see, I will move it to the left a bit. Yes, this is tau t naught x naught. Now, it is, see what I have done, I have first differentiated with respect to phi and then differentiated phi with respect to x naught. Okay. So, we have got this term and this term multiplied together, we have done it in two parts, and this can be written as I will write this as a it will be a function of tau and x naught. So, ultimately what we have is that this is equal to I plus integral of t naught to t. This is a matrix. So, this is a matrix of tau x naught times tau t naught x naught by, right. So far so good, we have differentiated this and have obtained this. Now, this term what is it saying? It says that if I perturb it, how much will phi change? Phi is this function, and naturally this phi I have to answer the question, is it here or here or here, right. So, if it is here, then if I perturb it, it will change by some amount. That means, you obtain the derivative of phi with respect to x naught computed at this point at something, computed at this point it will be something else, computed at this point it will be something else. So, actually what I mean to say is that this derivative is actually a time varying quantity. This derivative is not a fixed thing, phi as a function of t. So, this term will actually keep on varying. So, in order to find out how it varies, we need to take a derivative of this. So, what we will do is, we will take a d dt of this term with respect to x naught. Now, in the right hand side, it was I, which when differentiated with respect to t will vanish. Here is a integral over time, which when differentiated over time, this integral will go, and we are left with only this. So, it is actually a large simplification a t x naught, and this will be phi t naught x naught, this will be in terms of x naught. So, what is this? Here is a term which also appears in the right hand side. Here is a derivative, here is not a derivative. What does it mean? It means it is a differential equation. Imagine this whole thing, if you call it say p, it is dp dt is equal to a times p. it is a differential equation. But here the terms are all matrices. So, it is a matrix differential equation. So, it is a differential equation where terms are all matrices. So, it is a matrix differential equation, but nevertheless conceptually you can solve it. As a result, you can obtain this term. So, as a result you can obtain this term. What does this term say physically? It says that how does the function change with time as you change the initial condition. This function goes around, so that will be a function of time. So, this is a function of time. Okay. So, when you solve it, ultimately when you have obtained that this term, you have obtained that as a function of time. If you have obtained that as a function of time, this fellow has been obtained, then everything is simple, because now we will say that this distance is, say, delta phi. So, this distance is delta phi, here is the phi and here is the delta phi. That means, the perturbation itself is called delta phi. So, then we can write delta phi of t naught x naught. That means, the perturbation as it travels through time is then written as this term t naught x naught y. How is it changing with time? Times the initial t naught. This is the initial perturbation times this term gives the final perturbation. Clear? So, this is nothing but there will be plus higher order terms. So, this is nothing but a sort of a local linearization of the evolution of the perturbation around this original trajectory. So, what have we done? We have obtained this matrix differential equation whose solution, this fellow as a function of time is called a sensitivity function, which means that this says that if I have the initial perturbation this much, then I can multiply that by the sensitivity function to obtain the final perturbation in the first order approximation. Clear? There will be higher order approximations also. I do not want to go into that, but in general the idea is that I have my initial perturbation and the perturbation travels through time, and the travel through time is simply represented by the multiplication by a factor which is the sensitivity function. Now, that sensitivity function, if that goes to 0, you know that the original trajectory and the perturbed trajectory converge. Clear? So, that is the concept of the sensitivity. There is a concept of sensitivity. Fine? Is that clear? Okay. Now, this sensitivity idea is general and applicable to any given system. It is general enough and applicable to any given system. The only issue here is that in case of your switching systems, where you have an orbit going like this and then going some other way and then going like that, there we need to do something about this process. That means, we will need to figure out how the sensitivity function goes across the switching surface. We will do that later, but presently the basic idea is that in case of orbits like this, say I have got an orbit like this, closed loop, as it happens for say any oscillator. So, that is an orbit. I have the state space like this, and then how to figure out the stability of this orbit, we will say that we will part of this initial condition say to this point, and we will try to figure out how it goes. Now, in order to figure out, the simplest possible way is to find out the sensitivity function. So, that if I now know the initial perturbation, I can find out the perturbation after any length of time, because the final perturbation will be nothing but the sensitivity function at that time times the initial condition, initial perturbation. Okay. So, that is the concept with which it all came. Now, it is clear that it is somewhat difficult to actually pinpoint, obtain the sensitivity function as a collection of numbers. It will be somewhat difficult, right? I mean, conceptually it is fine. Conceptually writing things like this is fine, but ultimately if I ask you to figure out how these numbers are obtained, this is nothing but a matrix with numbers. How would you obtain these numbers? It is not easy to figure that out in a general nonlinear system. So, we need to have some kind of a method to do that. Now, you notice that okay, at this stage I will take you to the idea of at this stage it will be good to have a look at the idea of Floquet. Let us go directly to the Floquet's idea. Okay. Floquet said, remember he was about 100 years back. So, very old piece of work, but a masterpiece of work. He said that instead of considering the perturbation and the evolution of the perturbed trajectory, if you consider the perturbation itself, that means this vector itself. Earlier what we are doing, we started from an initial condition and the perturbation, and we tried to figure out how the perturbed trajectory moves. Instead, he said that okay, let us consider instead the perturbation as a vector and its evolution. So, the perturbation is, initial perturbation would be T is the original trajectory and the perturbed trajectory. So, x the periodic orbit okay, for the perturbed trajectory minus the original trajectory. Sorry, I am using the subscript p because now we are talking about periodic orbits. There is a point in talking about the stability of periodic orbits only. If it is not a periodic orbit, obviously it does not have the stability. So, we are trying to figure out the stability of periodic orbits, and that is why I am using the subscript p. So, here is the perturbed trajectory minus the original trajectory is the perturbation. Sorry, this will be x of t. The perturbation itself is just this. Okay. And then in terms of that, if you write that linearized equation, it obviously takes the form d dt of delta x t is equal to, it will be a coefficient times the initial perturbation, that would be f of x t times calculated at times delta okay. So, you can write it as a of time and the part depending on the trajectory itself times delta x. Now, what does this equation say? It says that the perturbation its derivative with respect to time is some factor times the perturbation itself. So, this is also a differential equation. Here how it moves. Had this a been a constant term, it would be trivial to solve for this, how the perturbation moves, but unfortunately this a term is a function of time. See what it is saying, it says that suppose I have got a trajectory which is a periodic orbit. So, this is x of p. Now, I am considering a perturbation from there, and I am trying to figure out how this perturbation is evolving as time progresses. So, it is like this, but I am not talking in this case about the perturbed trajectory, I am talking about the perturbation itself, how it is evolving. So, we are writing a differential equation in terms of the perturbation. This is the differential equation in terms of the perturbation, but then after having written so, that means here we have sort of linearized it around that periodic orbit. As a result, we have obtained this, which is fine, but then this fellow is a function of time. We have difficulty here. We cannot really directly solve it, and people before Floquet were stopped at that stage. Floquet proposed the great insight without proof. He actually did not prove it, but later it was proved that this A is a matrix here. This is a vector, this is a vector, and A is a matrix. This matrix will be time varying, all right, but that time variation will be periodic in time. That means, this A, as it goes around the periodic orbit, this will have the same value. That means, you see, imagine that A is a 3 by 3 matrix. Imagine that there will be something here, something here, something here, something in these positions, and all these will be time varying quantities, but all these will be periodic in time. These numbers will change and it will have periodicity, a periodicity the same as the periodicity of that original orbit. As a result of which, he said, if you observe it say once every cycle, all these will be constants. Okay, it is a great insight. It is a great insight. He said that these numbers will be all time varying numbers, all right, but do not get disturbed by that. You only need to observe it once every cycle, then all these will be constants. Every time it comes back to the same position, these will be constants. Okay. And when you further probe that idea, that means here you have a periodic orbit, which according to him you observe once every cycle, it becomes the same as a Poincare section, right. So, what you learnt as a Poincare section and the concept of stability of the fixed point on the Poincare section is the same as the stability of that periodic orbit as per Floquet. Fine. So, essentially then the problem becomes how to obtain this particular thing once every cycle, which as I said, these will become constants then. These are actually time varying, but when you observe it every time on this particular plane, it will be constant. So, forget about this time variation, try to figure out what will it be once every cycle. So, from this point of view, essentially the crux of the problem becomes to find out delta x of t, where t is the whole cycle, is equal to phi, the function, t plus t naught is the final time, t naught is the initial time, and delta x naught is the initial perturbation times delta x naught. So, the essential problem becomes to figure out this value. Okay. So, once you start from an initial perturbation and come over the whole cycle, okay, that means you start from an initial perturbation, say here, and you come over the whole cycle, you say come here, then the initial perturbation is this much, the final perturbation is this much, initial perturbation is here, the final perturbation is here. Okay. Then you have to express it as the final perturbation is equal to something times the initial perturbation, and that something has to be found out. If this is a vector, this is a vector, this will be a matrix. So, the problem boiled down to finding this. The problem boiled down to finding this. Now, this fellow is called the monodromy matrix. So, monodromy matrix is nothing but the matrix with which the initial perturbation has to be multiplied in order to get the perturbation after a whole period. So, it essentially embodies the evolution of the perturbation over a whole cycle. So, that is the monodromy matrix. Now, you have come across the concept of state transition matrix. Those who have done some course in control theory have done something on state transition matrix. What is state transition matrix? State transition matrix is essentially that this phi of t, t naught, x naught. That means, this is the solution of the set of differential equations. That solution can be written as a combination of linearly independent solutions, and those linearly independent solutions can be phi 1 of t, t naught, x naught, comma phi 2 t, t naught, x naught, and so on and so forth. These are the linearly independent solutions, and the final solution, the actual solution, is written as a linear combination of these. Now, out of these possible solutions, or possible phi I of t, t naught, x naught, there is only one that satisfies the condition that phi of substitute in place of t, t naught, x naught. What should you get? What should you get? This is the final condition is equal to this times the initial condition, and here the final time is the initial time. So, this fellow must be the identity matrix. So, this is I. So, there is only one out of these that satisfies this condition, and this matrix is called the state transition matrix. So, in general, the state transition matrix has the property that if you have a travel from this point to this point via this point, so we will say this is say x a, and this is x b, and this is x c. This state travels in the state space through this, then we can write that x b is equal to the state transition matrix a b times x a. So, this is the role of the state transition matrix, that it takes the state to the state later. Okay, fine. And if you can write that, then you can also write delta x b is equal to phi a b delta x a, means if you perturb the state and the perturbation travels, then the perturbation at this point is also related to the perturbation here by the state transition matrix. So, it not only state transition matrix not only relates the state initial to the state final, but also it relates the perturbation from the initial state to the final state. Clear? And then if this fellow travels like this, so you can also write x c is equal to phi b c x b, and we can also write delta x c is equal to phi b c of delta x b. If these are true, then you can also write delta x c is equal to phi a c x a, and okay, and in that case your phi a c is, yes, sorry, phi a b into phi b c, delta x a. So, if you travel continuously from x a to x b to x c, then you can write this, and then the final perturbation, how the perturbation evolves from a to c is given by this, and these two state transition matrices are simply multiplied together to obtain the state transition matrix from here to here. Okay. Let us stop here, and we will continue in the next class after this, from this point.